The first photographs from the surface of Venus weren't supposed to exist. Scientists had calculated that nothing could survive down there long enough to transmit a single image. They were almost right. In the mid-20th century, astronomers thought Venus was a tropical swamp world. The thick clouds suggested humidity. Dense coverage meant shade from the sun's heat. Some even speculated about Venusian jungles. Early Soviet missions launched with sensors calibrated to detect water and measure rainfall. The reality was inverted. That cloud layer wasn't protecting the surface. It was sealing it like a pressure cooker lid, trapping heat in a runaway greenhouse effect that pushed temperatures to 475 degrees Celsius. The first probes didn't malfunction. They were physically crushed by atmospheric pressure before reaching the ground, imploding at altitudes where they should have still been safely operational. This created a new scientific consensus. Even if you could armor a probe enough to survive the descent, photography would be pointless. The atmosphere was 90 times denser than Earth's. Light couldn't possibly penetrate that depth. The surface had to be locked in absolute darkness. Soviet engineers ignored this model entirely. They equipped Venera 9 with floodlights just in case, but programmed the camera to scan immediately upon landing, regardless. When the data came back, it proved the darkness theory completely wrong. But what really disturbed scientists were the later panoramas from Venera 13. Those images contained details nobody has fully explained, even today. The engineering failures that preceded success reveal how brutally hostile Venus actually is. In 1967, scientists estimated surface pressure at 20 times Earth's atmosphere. High, but manageable, with reinforced aluminum. Venera 4 was built to those specifications. It deployed its parachute expecting a controlled drift downward. At 27 kilometers altitude, the transmission flatlined. The probe hadn't burned up. The atmosphere physically crushed it like an aluminum can, nowhere near the surface. This revealed the catastrophic scale of their miscalculation. Pressure wasn't 20 times Earth's. It was closer to 90. Standing on Venus is equivalent to being a kilometer underwater in Earth's oceans. They had months before the next launch window. Not enough time for a complete redesign. So they attempted a workaround. Venera 5 and 6 used smaller parachutes. The logic was simple. Fall faster, spend less time exposed to increasing pressure, maybe reach the surface before structural failure. Both probes imploded 11 kilometers above the ground. This forced a total philosophical shift. The engineers stopped designing a spacecraft and started building a submarine. Venera 7's new design featured a forged titanium sphere rated for 180 atmospheres, double the expected maximum load. They stripped out almost every scientific instrument to save weight for armor. Windows were eliminated, solar panels replaced with heavy internal batteries. It launched in August 1970. During descent, the parachute reefing cords melted. The parachute failed. The probe didn't float down. It fell, impacting the surface at 17 meters per second. Mission Control watched the telemetry stream die instantly. Another failure logged. Only during post-mission analysis did someone notice patterns in the static on the raw radio tapes. The probe hadn't died. It had toppled over on impact, pointing its antenna away from Earth, but it was still transmitting. By processing the noise, they recovered 23 minutes of temperature data from the surface, the first human machine to successfully communicate from another planet's surface. It confirmed the 400 75-degree nightmare. It also proved something could be built to survive it. But surviving meant more than just withstanding pressure. The temperature problem was equally catastrophic. At 475 degrees Celsius, lead melts, zinc melts, tin melts, standard silicon electronics vaporize instantly. You can't simply insulate against this. Insulation only delays heat transfer. Eventually, thermal equilibrium wins. Active cooling systems like radiators won't work either. A radiator dumps heat into cooler air. On Venus, the exterior air is hundreds of degrees hotter than your machinery. The solution was to turn the entire lander into a temporary heat sink. Before separating from the orbiter, the system circulated supercooled fluid through the pressure vessel, dropping internal temperature to -10 degrees Celsius. The probe essentially began its mission as a block of ice falling into a furnace. To handle heat generated during descent, engineers packed the interior with lithium nitrate trihydrate. This chemical has a melting point of 30 degrees. When substances melt, they absorb massive amounts of energy without rising in temperature. As Venusian heat penetrated the titanium shell, it went into melting the lithium nitrate rather than frying the electronics. This bought roughly 50 to 60 minutes of operational time before the system boiled over. The camera itself required a completely different approach. Television cameras from the 1970s used cathode ray tubes, large, fragile, requiring glass lenses that would shatter under external pressure. You couldn't risk mounting a large glass window in the pressure vessel wall. Structural failure there meant immediate implosion. Instead of a camera, they built a telephotometer, a mechanical scanner, rather than a lens-based imaging system. The device remained safely inside the cooled titanium sphere, looking out through a tiny cylindrical quartz window thick enough to withstand the pressure. A small mirror rotated behind the window, collecting light from a single point and directing it into a sensor that measured brightness. Then the mirror moved slightly. Next dot, next measurement. The probe didn't transmit video. It sent a stream of numbers that Earth computers reconstructed line by line over many minutes. On October 22nd, 1975, everything changed. Venera 9 survived the descent and transmitted data for approximately 50 minutes. It landed on a steep slope of roughly 20 degrees. Engineers had prepared for the worst-case scenario regarding visibility. They assumed thick clouds would block all sunlight, plunging the surface into deep twilight or total darkness. To counter this, the lander carried powerful halogen floodlights to illuminate the ground in front of the camera. When the lens cover popped off, the sensors detected immediate illumination. The floodlights were unnecessary. The surface of Venus was not dark. Ambient light levels were comparable to a cloudy summer day in Moscow. The thick atmosphere scattered sunlight evenly, creating a soft, diffuse glow that eliminated harsh contrasts but provided plenty of light for the telephotometer. The camera began its scan. It took 30 minutes to build the full panorama. As data arrived on Earth, scientists saw something that contradicted years of theory. They expected a sandy desert or landscape worn smooth by erosion. The atmosphere was dense, so they assumed strong winds would scour rocks down to pebbles. The image from Venera 9 showed the opposite. The ground was covered in sharp, angular rocks. Edges were jagged and broken. This implied the surface was geologically young. It also proved wind speed at the surface was negligible. The rocks had not been eroded by wind or sand. The atmosphere was calm. The image also revealed clarity near the ground. There was no fog or dust. The horizon was clearly visible in the corners of the panoramic frame. The probe was sitting on a pile of tectonic debris, likely from the landing itself or recent geological activity. 3 days later, Venera 10 landed over 2,000 kilometers away and operated for 65 minutes. It touched down on a much older, smoother plane. Its images showed flat slabs of rock resembling dried magma flows. The difference between landing sites proved Venus was not a uniform wasteland. It had distinct geological regions, mountains, slopes, and plains. The primary discovery, however, remained the light. The fact that sun could penetrate 90 atmospheres of carbon dioxide showed significant diffused sunlight reach the surface, contradicting earlier predictions of total darkness. These two black and white images were the first direct look at the surface of another planet, but they were limited by their lack of color. Scientists could see shapes, but they couldn't see the true nature of the chemical world they had touched. In March 1982, the Soviet Union launched Venera 13 and Venera 14. These probes represented the apex of the program. Heavier, smarter, carrying more instruments than predecessors. The primary goal was no longer just proving the surface existed. The goal was characterizing it chemically and visually. To do this, engineers upgraded the telephotometers to capture color. Venera 13 landed on March 1, 1982, and survived for a record 127 minutes. It began scanning immediately. The camera didn't take a single color photograph. Instead, it took multiple scans using red, green, and blue filters. Data was recombined on Earth to create a composite color image. The result was startling. Black and white images from 1975 had shown a stark, rocky world. The color images revealed a landscape bathed in a suffocating, deep orange glow. There were no other colors. Rocks were orange. Sky was orange. Horizon was orange. This wasn't a malfunction. It was atmospheric physics. The atmosphere of Venus is so thick it acts as a massive filter. It absorbs blue and green wavelengths of sunlight as they pass through the clouds. Only red and orange wavelengths reach the surface. To verify this, the lander carried a color calibration chart within the camera's field of view. The chart contained strips of white, red, green, and blue paint. In the transmitted image, the white strip appeared orange. The blue strip appeared almost black. This proved a human standing on Venus would see the world in sepia tone. The brain would not be able to correct the scene because there's no white light reference. Venera 13 also broke new ground in audio. It carried a microphone designed to detect seismic activity and atmospheric discharges, but it also functioned as a standard audio recorder. It captured the first sounds ever recorded on another planet. The recording revealed two distinct types of noise. First was wind. Telemetry indicated a wind speed of roughly half a meter per second. On Earth, this is barely a breeze. On Venus, air is 60 times denser than Earth's atmosphere. A wind moving at half a meter per second pushes with significant force. The microphone picked up a low, constant aerodynamic drone as thick air flowed over the lander structure. The second sound was mechanical. The probe successfully deployed a pneumatic drill to collect a soil sample. The microphone captured the sharp, explosive sound of the pyrotechnic charge firing the drill mechanism. It then recorded grinding noise of the bit cutting into basaltic rock. This audio confirmed the dense atmosphere was an excellent conductor of sound. The environment wasn't just hot and pressurized, it was noisy. Venera 14 landed 4 days after its twin on March 5, 1982. It touched down in a flatter region roughly 1,000 kilometers away from the Venera 13 site. The terrain here resembled cracked pavement of basaltic rock. Mission objectives were identical: photograph the surface, analyze the atmosphere, and physically test the ground. One of the key instruments was a spring-loaded arm, designed to swing out and strike the ground with known force. By measuring how far the arm penetrated the soil, scientists could determine physical density and compressibility of the Venusian surface. A simple mechanical test intended to tell us if the ground was soft dust or hard rock. But something went catastrophically wrong. The landing sequence was automated. First, the probe secured its footing. Second, cameras began operation. Lenses were covered by titanium caps during descent to protect optics from heat and pressure. Once on the surface, pyrotechnic charges fired to eject these caps. Caps popped off, clearing the view for telephotometers. On Venera 14, the lens cap ejected exactly as planned. However, it didn't roll away. It landed directly on the spot where the compressibility arm was programmed to strike. A few moments later, the arm deployed. It swung down and hammered the object directly beneath it. Telemetry sent back to Earth indicated the surface of Venus was incredibly hard and rigid. It showed zero compressibility. This was technically accurate data. The probe wasn't measuring soil. It was measuring the titanium lens cap it had brought from Earth. The camera scanned the area and sent back an image confirming the failure. The photograph clearly shows the arm pressing firmly down on the center of the discarded lens cap. The actual surface of Venus lay only centimeters away, untouched. The incident remains the most famous mechanical failure in the history of the program. It highlighted immense difficulty of remote operations. Engineers had successfully navigated millions of kilometers of space, survived re-entry, and landed in hell, only to be defeated by a piece of their own safety equipment. Mission data sat in archives for 30 years. Scientific consensus remained that Venus was sterile. Surface temperature and pressure made organic chemistry impossible. In 2012, however, Leonid Xanformality published a paper challenging this view. Xanformality wasn't a fringe theorist. He was a respected contributor to the original Soviet space program. He decided to re-examine the raw panoramic sequences from Venera 13 using modern digital image processing techniques. His analysis focused on the timeline of images. Telephotometers didn't take a single snapshot. They scanned the scene repeatedly over the course of the probe's life. By aligning these sequential scans, Xanformality looked for changes between frames. He found them. He identified several objects that appeared to behave erratically. The most prominent anomaly he named the Scorpion. In early scans, soil is empty. In a scan taken 7 minutes after landing, a structured object appears. It's approximately 15 centimeters long. It seems to have a central body and a curved tail. In subsequent scans, the object is gone. Xanformality argued the object emerged from soil, remained visible for a short period, and then moved out of frame. He also identified an object he called the black flap. This object appeared to change its shape and position relative to the probe. He stated these objects emerged, fluctuated, and disappeared. He suggested inhabitants of Venus might utilize a form of life based on exotic chemistry rather than carbon and water. The global scientific community rejected his conclusions. NASA scientists and other Russian experts provided a mechanical explanation for anomalies. They argued the scorpion and the flap were likely pieces of the lander itself. The probe was wrapped in layers of insulation and plastic. As internal temperature rose, these materials began to melt, peel, and fall off. Movement wasn't biological. It was the result of the lander disintegrating under thermal stress. Shifting shadows were likely caused by the changing angle of sun or settling of the lander into soft soil. Subsequent analyses and improved image restorations have confirmed these features as artifacts, noise, or detached components of the lander, rather than evidence of life. Despite rejection of the biological theory, the analysis revealed something unsettling about the footage. The surface of Venus wasn't a static painting. It was a dynamic place. Things moved, debris shifted, the lander groaned and warped. The footage didn't show a dead world. It showed a violent interaction between machine and environment. The impossible shapes were likely the dying convulsions of the probe itself, captured in slow motion by the scanning camera. The camera on Venera 14 was the last eye humanity opened on the surface of Venus. After 1982, Soviet priorities shifted. Engineers realized landing in random spots provided excellent close-up data, but it couldn't map the entire planet. To understand geology of Venus on a global scale, they needed to see through clouds from orbit. Venera 15 and Venera 16 launched in 1983. They didn't carry landers. They carried massive synthetic aperture radar systems. These probes mapped the northern hemisphere. They revealed shield volcanoes, lava channels, and tectonic fractures. The data was scientifically invaluable, but it was abstract. It was a topographic map, not a photograph. The final Soviet missions to Venus, Vega 1 and Vega 2, launched in 1985. These were hybrid missions designed to intercept a comet. They dropped off landing units at Venus on their way. These landers focused on soil chemistry and atmospheric analysis. They also deployed balloons that floated in the upper atmosphere to measure wind speeds. They didn't carry cameras. Engineers decided weight of imaging system was better spent on other instruments. With collapse of the Soviet Union, the program ended. Today, restored images remain the only direct ground-level optical photographs ever taken of the Venusian surface. Subsequent orbital radar missions and recent observations, including near-infrared detections by the Parker Solar Probe that sensed faint thermal emission from the surface through atmospheric windows, have added valuable new perspectives. However, no mission since has returned new photographs captured from the surface itself. Every other image of Venus you see is either a radar map, an artistic rendering, or a photo of cloud tops. We've sent rovers to Mars that stream high-definition video daily. We've flown past Pluto, yet for the planet closest to Earth, our visual understanding is frozen in 1982. We rely on data collected by a titanium sphere that melted 40 years ago. Until a new lander survives the descent, the yellow rocky plains of the Venera panoramas remain our only true view of hell. The disturbing secret isn't what we found on Venus. It's what we lost the ability to see. NASA has proposed new missions. Da Vinci will drop a probe through the atmosphere in 2029, but it won't carry a camera pointed at the surface. The European Space Agency's Envision will orbit and use radar. Russia announced plans for Venera D, a lander that would finally return new photographs, but funding remains uncertain and the timeline keeps shifting. The technology to survive Venus exists. We proved that in 1982. What's missing is the will to go back. Meanwhile, those orange panoramas from Venera 13 and 14 sit in archives, still hiding details we haven't fully processed. Each time someone applies a new restoration algorithm, they find features that weren't visible before. Textures in the rock, patterns in the soil, shapes that may be debris or maybe something else entirely. The footage is 40 years old, but we're still not done analyzing it. And until someone builds another machine capable of landing in that crushing heat and transmitting before it melts, those grainy scans from a Soviet titanium sphere remain the only window we have into the most hostile landscape humanity has ever photographed. Venus isn't keeping secrets from us. We're just not looking anymore.